Good afternoon, everyone. Welcome to the last session of Star Trek 2022. And in just over an hour and a half, it will be movie sign. Yep, we got movie sign. So I hope everyone here is wanting to, be here for fun, etc. I apologize for sitting down on the job. I'm recuperating from ankle surgery, and so I'm not exactly ambulatory at this point in time. But let's get started. My name's Matt Williams. You may have seen me in various and sundry other conferences or users groups or whatever. I kind of make my way around. The illustration is by my daughter. It's now about 7 years old, and I have yet to persuade her to, update it for me, unfortunately. She's starting to see dollar signs in her eyes. And you mean you wouldn't do it for your good old dad? No. So why am I here? Well, this basically started out with me having a Raspberry Pi problem. Hi, my name is Matt. I have a Raspberry Pi problem. And I was in the process of searching for real work for my Pi cluster. So my Pi cluster consists of a tackle box about yay by yay by yay that's got rack-mounted Raspberry Pis in it, and a 24-port gigabit switch, SSDs, a router/firewall, and just sitting there, it's pulling under 50 watts. And it's got about 20 Raspberry Pis in it. So in the process, though, and working with the limitations of Raspberry Pis, I've discovered some really nifty data structures and algorithms. And hopefully, a lot of these are ones that you haven't heard of. One of them actually is from 1976. And I was kind of gobsmacked when I saw that, because I'd never heard of it before. First off, I am not a mathematician. I'm not a chemist. I'm not an expert. I am very, very passionate about data structures and algorithms, and I'm hoping that I might be able to infect some of that passion in some of you. So, there will be a quiz. I'm going to give you the quiz question right now, and then at the very end, see if anybody might have the answer. So, in computing, there is one data structure that rules them all. It's used by every single program in every digital computer. So give it some thought and see if you can think of what it might be. So good algorithms matter. The reason behind choosing a good algorithm is that the good ones tend to break the problem into smaller problems or are very focused. They're only going to do what you need to reach an answer. There is no best algorithm. Putting on an architect's hat, I will say, when asked what algorithm to use or what data structure to use, it depends. And there's no silver bullet, as I was just saying a moment ago. So why do we want to study data structures and algorithms? Well, if all you have is a hammer, you're going to try and brute force every single solution. If all you know is, say, for instance, Java collections, everything then becomes a collections problem. And then you end up having hashes of hashes of hashes. Anybody ever encounter those in somebody else's code? Not your code, somebody else's code. So each algorithm has a sweet spot where they work best. And you know what? Sometimes a sequential search is the best search. But the considerations that you need to take as to which one is most suited for your particular application here is space, runtime, what sort of data it's accessing. And actually, I'd like to add another bullet point here, and that would be how hard is it to maintain? Being clever costs a lot of money. And I'd like to introduce the idea of maintenance-driven development. This is the idea that, 3 months, 6 months, a year, 2 years from now, you're the one who's going to get the call in the middle of the night and have to figure out what you wrote. Or, better yet, the poor sod who gets the call knows where you live. So the key is knowing your data. Everything we do in IT ultimately manages data. You have input, you do something to it, you output it. If you don't know your data and don't know what you're getting and what you're supposed to be giving, then you really can't write programs effectively. And, like sand through the hourglass, so is the data of our lives. Everything streams by us. We might touch it. We might do something with it. So now we're going to touch on a topic that might make people a little uncomfortable if they remember, first year computing or what have you, namely the big O. Anybody ever hear of that? Yeah? Cool. So it refers to the complexity of an algorithm. You can also think of it in terms of the number of cycles, comparisons, or steps that you need to complete a task. So we're going to go through a number of algorithms here in just a moment, talk about them, and find out where they're sweet and so forth. So first off, we have linear time. And linear time is something that each time we run it, we have the number of cycles for the size of our data set. Then we have quadratic time. Quadratic time gets expensive pretty quickly. You may have heard of a bubble sort, for instance, where the values just kind of bubble up to the top. Bubble sort is one of those that would be considered n squared. Then you have O of n of log n. If you notice, as the size is increasing here, our number of cycles that we need to process this are not increasing by a whole lot as compared to quadratic time or even linear time. So 1,000 invocations in linear time needs 1,000 cycles. In n log n, it takes a few. In log of n, our 1,000 cycles takes 10 to run through, roughly. So by comparison, if you remember at the very beginning, I said that good algorithms cut down on the amount of processing that you have to do, or they really focus on what you're doing. Log of I is even faster. 1,000 is 3 cycles potentially. And then if you want to get really, really crazy, we have log of logs. So just the character up there, anybody ever hear of Redwall? And so back a while ago, they made a Redwall cartoon, and that character's name is Log-a-Log. And this is a nod to my daughter, because she really enjoyed the Redwall cartoons. So if you look with the log of log for having 1 billion cycles, or 1 billion elements, it takes 3 cycles. As opposed to 1,000 for logarithmic time, that takes the 3. This is part of why having good algorithms matters. But again, don't get so caught up in finding the best algorithm that you spend weeks and weeks and weeks developing something that can't be maintained. And then we have constant time. No matter what you do, it takes the same amount of time. So we're going to go through some various and sundry searches here, different types. I want to give a disclaimer. I used a random number generator to generate these numbers. I did not fudge the numbers. I also used a random number generator to pick the one that we're looking for. I did not fudge the numbers. You'll see why I'm putting this disclaimer out in a moment. So if we're looking for 812 out of our set of numbers that we have here, let's go linearly. Well, is it greater than 1? Yeah. Greater than 22? Yeah. 47, 135, yada, 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 yada. And finally, we hit our 812. So that, it had approximately 10 different steps we had to go through to get there, which may not be bad. If this is a batch job that's running once a month and you only have a small number of elements that you're cycling through, sequential sort or linear search may just be a good solution for you. So next most common search that people are probably familiar with are binary searches. In a binary search, we're cutting our space of values in half at each time. So we start in the middle and say, okay, is 812 higher or lower than the number we're at? Well, it's higher, so we're going to split the difference again. And it's still higher, so we're going to split the difference. But this time, it's lower. So we come back, and we're at 812. So we've gotten to our number, but it took us 4 or 5 steps to get there. It's still better than what sequential was, but there are better searches. One of these is the Galloping Search. One of the problems with a binary search is both sides have to be bounded, because you need to know, all right, where's the middle? If you don't know how far this one goes on the right-hand side, or my right-hand side, your left, then you can't rightly do a binary search. What the Galloping Search does is takes a window, and it slides the window through your data set. It's really good for things like searching a log file, if the log file is constantly growing. Or you can actually, if you know that your data that you're searching for is either towards the beginning or towards the end, that's another sweet spot for this type of search. And it approaches log of I. So let's take a look and see how it works. We start out with a window. Our first window is 2 to the 1 long. And, well, 812 is greater than 22. So let's create another window. And our upper bound, this time, is 333. Well, we know that 812 is greater than 333, so let's do it again. Each time, we are creating a larger window. Then once we find something that is within our window, we can then do a binary search in order to find it. So let's see where galloping is going to beat binary search. So if 22 is our target, binary search takes 3 steps to see that where 22 is. So we have a first where we come in the center, and then our second cuts that in half, and then our third cuts it in half again. Whereas in this case, with the Galloping Search, we have our initial window, and we happen to find that the upper end of our initial window is 22. So the Galloping Search in this case took 1 step. That's part of why it's really good for things that you think are going to be at the beginning or the end. Or, again, for things that are unbounded. So if it's looking for 13, our binary search is going to take 4 steps before it realizes that, oh, we don't have 13 in our set of data. Likewise, again, galloping finds it's not in there immediately because it knows that our first window has 2 elements and that they're 1 and 22. None of them are 13. Out of curiosity, anybody ever encounter this searching algorithm before? Ah, 1 person. Wow, that's a first. Cool. So a variant, you can start at the other end. It works the same way. Or you can do a trot, where the indexes grow not exponentially, but by some value. So 1, 3, 6, 10, etc. You could have it grow by a Fibonacci number if you wanted. Basically, once you've overshot the number, then you can dial back in. So Galloping Search in some cases is really useful, but there's another search that is much, much, much faster. And it is the Interpolation Search. So anybody ever, I'm speaking to the older people in the audience here, but there used to be these, before Google and such, there used to be these books that were called dictionaries. And so, you want to look up a word. Do you open it to the middle and then, oh, no, it's not here, so you go to the next? Do you do a binary search on a book? No. You make a guess, right? And this is the Interpolation Search. So instead of splitting our area each go, we are going to make a guess. So with the Interpolation Search, it assumes that we have a distribution of data that is the same across the board. If we don't have a distribution, then it will basically become a binary search at the end of everything. So if it's 1, 2, 3, 4, 5 and you're trying to search that, and you think that the numbers may go up to 100, and you're looking for 10 or whatever, then this will approximate the same as a binary search. But in its best case, it's going to give us log of n. Now, do you remember I said I didn't fudge the numbers? If you remember, I said I chose this all randomly. So our predicted location in our interpolation search is the number that we're seeking divided by the maximum number in what our universe of numbers has divided by the size. So our first checkpoint in this case happens to be the right one. This really surprised me when I was putting the slides together, that it worked out that well. And that's why I go on to say, no, I did not fudge this. But it just happens to work very, very well. So to summarize our searching algorithms that we have here, we have linear that took 10 checks or 10 cycles to get there. Our binary and our galloping searches took 4 each, and that's dependent on the data. If we had different data, galloping would have been faster than binary. It all depends. And then our interpolation search was one cycle. We got there immediately. So let's switch gears a little bit and talk about some data structures. There are data structures that are not appearing today. I think everybody at Star Trek this year is Americans. In the past, there have been people from other parts of the world here in Star Trek. But we're not going to talk about queues, because Americans can't queue. And we're also not going to talk about stacks either. But we're going to start off, we've got arrays. And we've seen this array previously. We have linked lists. So with the linked list, each element has a pointer to the next element. It's relatively easy to insert elements compared to our linked our array, where we have to physically move everything. But with the linked lists, all we know is the next one. So we can only search a linked list sequentially. Inserts are easier than an array. Appending is going to be a lot more expensive. Because with an array, you say, oh, okay, I know where my end is. I'm just going to add our element at the end. Whereas with the linked list, you have to go through and find the end. Your traversal's linear, and you might think of it as being like a one-way street. With doubly linked lists, in this case, you point to the one before you and the one after you. Your inserts are less complex than with an array, but they're going to be more complex than a linked list. And I apologize if this is a review for some of you. We are soon going to be hitting some data structures that I'm willing to bet people haven't seen before. Your appending becomes more complex. Your traversal is still linear, but this is a two-way street. And then you have ring lists, where you go through and it loops back to the beginning. A doubly linked ring list means it's going to be very easy to append things at the very end, because you know from where the first one is, where the end is, and then the one before. So you can just append things easily there. Sometimes a ring list is implemented as a fixed size array. In these cases, they would be generally used as buffers. So you start writing at the beginning, you just keep your pointer of where you are writing to, and you'll wrap around. Meanwhile, the person who's reading it is going and keeping track of where they're reading. The problem is, if you're adding things to your buffer faster than you are actually pulling things out from the buffer. If you've ever been in the before times, been to a deli counter, and now serving number, sometimes line might back up so much that they hit 999 and roll back around to 1, and 1's still standing there. Then we have trees. And I'm sorry, I know it's late in the day. Your minds are getting full. Brains are starting to leak out of the ears. I'm not seeing too many deer in headlights, but I actually have the deer in headlight thing going on for me. So, so I've got a number of not quotes in here. This was not by Joyce Kilmer. Just a really quick aside. If you ever get the chance to go to Joyce Kilmer, it's down in North Carolina. It is one of the last places on the East Coast that is virgin land, never been cut. And so it's like 500 acres, and there are fallen logs yay high. The log itself is just laying on the ground that high. And there's not many places like that left in the world. So if you get the chance, I would suggest going to Joyce Kilmer Forest. So our trees are built like a tree. We have a root, then we have branches, and then we have leaves. And these are really good for searching because we have a built-in binary search. The problem with the tree, however, is that it's hard to do inserts. And it's really, really hard to keep the tree balanced. This is a non-trivial problem in computer science. So, all right, it's time for a mini quiz break. We're about halfway through on my time. And so let's have a mini quiz. So I'm going to read this up aloud. It is from a book called The Wizardry Compiled. And it actually refers to a data structure. The idea behind it was some programmer got kidnapped, sent to a world where magic is real, and he found that he could do magic by writing programs. So he wrote his own compiler, as we do. He then got kidnapped, and people got brought in to try and finish the compiler. So what the heck is this monstrosity, and why did he name it corned beef? Jerry says the name is probably some kind of rotten pun. What does it do? Basically, it takes the value of characters of a demon's name, multiplies them by a number, adds another number, and then divides the result by 65353. Then it uses that result as a subscript in some kind of array. She shook her head again. Why 65353? You know, if this guy doesn't come back, we may never understand some of this stuff. So anyone want to take a guess as to what data structure they might be? Yeah, yes, it is a hash. And why 65353? Close. He said it is a large random number to distribute the keys. It's actually one of the largest, it's not the largest, but is one of the largest prime numbers that'll fit in a 16-bit unsigned integer. I know I'm showing my age here, but generally, when you are using a hash, your array that you're sticking the elements into is going to be an array of size, some prime number. And congrats, you're the first one to get that. Yeah, go you. So yes, it's a hash. And hashes are really good where you have a huge, huge, huge universe, but just a few number of values. So they're used for sparsely populated universes. It allows for a quick lookup of values. And again, oftentimes it's implemented with a space the size of some largish prime. So let's look at a hash. Here we have our hash, and we have a smallish prime number for our array. And so generally, hashing functions will map to a particular entity. So we've added in two elements. We have a 5, we have a 9. And then we're going to try to add 23, but it's going to collide. So what happens? We have a hashing collision. We have two different things that we're trying to stick in the same place. It doesn't work very well. So how can we handle these? Well, one way is to have a larger bucket or a larger hash table. But when you rehash, that's a relatively expensive thing because you have to go back through and recalculate the location of every element. Or you can use buckets. So with a bucket hash, where 23 collided with 5, we are actually going to start a linked list. And our linked list will have the elements at each of those hash locations. So we have some more things. And if you notice, our hash here is getting a little crowded, and some of the buckets are getting a large number. If you recall, our linked lists are searched sequentially. So, you know, if we're looking for X, well, we know it's going to be in the 9 bucket, But suppose that we chose a really bad hashing algorithm and everything is in the same bucket. Then our hash really breaks down and it causes issues. And when that happens, your bucket's full. So how might we handle this? How can we come up with something that works a little bit better when our hash might be full and we have lots of collisions? Well, one particular solution to this is a cuckoo hash. I don't know if anybody's ever heard of the cuckoo bird, but one of the things that cuckoos do is they don't lay their eggs in their own nest. They lay their eggs in a different nest. And the cuckoos are the highlanders of the bird world. So what they will do is they will push everybody out. So we're going to, this time, insert 23 again. When it collides with 5, we are just going to kick 5 out of our hash. We have another hash that we'll stick it into. So time passes. We've inserted a number of elements. We have 23, we have X, we have 5, we have B, we have 9, and so forth. We're going to add 101. Well, it's going to clash with B, and B collides with X. So we're starting to get a cycle here where we don't have enough elements left. So it's going to create a loop. Our advantages of the cuckoo hash, though, is it approaches constant time for inserts. How many times do you see an algorithm or a data structure that's constant time? Almost never, right? It also approaches constant time, or it is constant time for all intents and purposes, for the lookups. I think this is a really neat sort, or data structure. I got sorts and searches on the brain. I apologize. Now, the problems, though, are you need a certain amount of empty space. If not, you're going to have an eviction cycle that just sits there and spins. So part of your algorithm needs to make sure that you're not sitting there and spinning. And if you are going to be starting to do that, then you need to resize and rehash. That hash is not the only hope. There is another. So if our cuckoo hash makes a much better hash, well, the cuckoo's kind of an ugly bird. Let's come up with a pretty bird, the Peacock Hash. And so the way that the Peacock Hash works is it handles our collisions by adding extra smaller hashes. And this was devised for real-time switches, handling ARP lookups, inserts and deletes, and so forth. It is real-time, and it's also constant time. So let's see how that might work. So we have our first hash with the elements in it. Do I have it? Yep, I have a cursor. And then, when collisions happen, they get pushed into the second. And then if there's a collision in the second, it'll get pushed into the third. What they found in testing is that they only need 4 or 5 hashes in those switches. And each one of them, as you see here, gets smaller. To be able to handle millions and millions of ARP addresses that are being inserted and removed in real time, they found that they only needed 4 hashes, and the 4th hash only needed like 5 elements. I think Peacock Hash is pretty cool. Anyone else? Anybody ever hear of it? Okay. So let's talk a little bit about sets. And we will get back to the Raspberry Pi. I'm building up to it here. So there's different types of sets. There's unordered sets. It can be a list. It can be a hash. Your inserts are cheap, but retrievals, not necessarily. So basically you just, stick something on the end each time. You don't care, but trying to find everything can be a little more expensive. The thing about sets, though, is there can be only one. Sets cannot have duplicate elements in it. Arrays can. Linked lists can. It's kind of hard for a hash to have duplicate elements because they'd collide. But sets, by definition, can only have one of each element. Now, if you have a sorted or an ordered set, then your inserts can be very expensive. Your searches, however, we've seen different ways of speeding up searches in order to have efficient searches through our sets. You could store it as a tree, but again, remember, inserts can be very expensive in trees. So how do we do set intersections? If you want to do a comparison between two sets. Well, I looked at 3 different languages, and all 3 languages used a sequential search to get the intersections. They started at the beginning of each of them and worked their way through. All right, it's easy. It's easy to maintain. If you only have a few elements in your sets, great. It's not a lot. It'll work just fine. But what happens when you have a lot of data? What happens to O of n? It's going to grow and grow and grow. It's going to have whatever your largest size is. So is there a better way to do this? How about let's use a modified galloping search to come up with our intersections. Let's use maybe an interpolation to come up with our intersections. So there is a paper on, as it happens, using set intersections for text searching, that their adaptive and their interpolative algorithms are variants on the galloping and on the heuristic search. So they'll use sliding windows to check and see, all right, I've got this bit here, I've got a range over here. Is there a possibility that there might be a change or a collision, intersection between them in these ranges? No. All right, let's slide our window again. Let's make it a little bigger, and so forth. Then you take, whichever is going to be your smaller window. Is everything over here underneath our maximum, or is the maximum here underneath everything there? And so by using different heuristics and such, yes, your comparisons are going to be more complex, but you don't have to check every single element. So just doing a sequential here in their paper, the sequential by itself took 119 million, I think I'm reading that right, different checks. By having an adaptive search, they were able to narrow down their problem set. Then looking at, all right, let's start whichever is smaller and use that for our initial set. And, if we have the highest number in the small set, 100, and the highest number in the larger set is 1,000, well, we know there's potentially a huge amount in our larger set that we don't have to look at. And so we'll hit the end and we'll be done. And then if we use interpolation, we can speed it up further. And then they have some other algorithms here where they just do variations on the theme. And so they were able to go from 119 million comparisons down to 43, almost 44 million comparisons. So they cut down their problem space into a third, right? We're only doing about a third of what you had originally. I don't know about you, but I think that's kind of nifty. So now, getting back to the pies. I used to work at Chemical Abstracts. They are a not-for-profit data service company in the chemistry area. And I wanted to find something that was real work for my Raspberry Pi cluster, just to show that, these computers aren't toys. And to be honest with you, back 20 years ago, having a CPU, even if it didn't, a CPU with, and this on the older Pis, that had a gigabyte of RAM and, was a gigabit processor, that was basically a workstation. That was a supercomputer. So but times have changed. And, people look at these little credit card things and say, oh, they're toys. They really aren't. But you have to know what the sweet spots are. You have to understand your hardware. You have to understand your data. So I looked at doing Substructure Search, which is a non-trivial chem informatics problem. So for instance, if you have a set of data that has substances in it, I want a list of all of the substances that have a benzene ring with a double bonded oxygen off of it, for instance. So starting out, 69 million substances. That's non-trivial. We have 150 gigabytes of compressed data, right? Uncompressed, it's about 3 terabytes. Our Raspberry Pis could handle 400, and typo, not 400 gigabits per second, 480 megabits per second. So, and that is all the I/O on that machine. So, obviously the Pis are very I/O limited. So we have 3 terabytes of data to work through. What are we going to do? Well, first thing is, do we need all the data? Let's look at what we have and extract the pieces that are important to us. So there's a way of describing chemical structures called smiles. And smiles basically uses a string to describe a chemical structure. For instance, benzene would be C1, CC, CC, C1. And the ones there show where things loop back around. Generally, hydrogen's left out. Hydrogen's kind of off on its own anyway. But there can be more than one way to describe the same structure. That's the main problem with smiles. Smiles is text. All right, what do we use to search text? Remind you, I'm a gray hair. Anyone want to take a guess? Just shout it out. A magnifying glass. Yes, that is true. That is true. Especially in the age of COVID, I've noticed my eyes have gotten much worse. I don't know if it's because I'm getting older or just spending so much time in front of the screen. But yes, a magnifying glass. What I was looking for was actually grep. Anybody ever hear of grep before? Yeah. So, it works. It's, a well-known tool. And let's actually see for our basic prototype, will this work? I don't want to spend a whole lot of time on it. So my naive solution that I started with was 5 Raspberry Pis. Each had a subset of data. And the data had the ID number of the substance, the smiles, and a name. So we've taken that 3 terabytes of data and smushed it down to megabytes worth. And I used Docker Swarm to distribute the workload. You might wonder why I did not use, say, Kubernetes. The reason I didn't was Kubernetes doesn't support well ephemeral jobs. So I would, pass out a grep task, and it would complete and die, and Kubernetes started it up again. So I wanted, some sort of ephemeral task that would just run and be done. So starting out with our benzene ring with a double oxygen on it, we've got 2,500 results. And so these requests came into a master, and the master then sent the requests out to each of the individual slaves. The slaves, or the workers, then spun up a Docker container, did the results, kicked it back, and in 5 seconds, I found out that out of my 69 million elements, then I had a total of 2,500 results. Not bad. The next one, if you notice, there's a lot more results. There's 17,500, and it took about 3 seconds. If you notice, this is not scaling linearly yet. There is some overhead for kicking off the Docker containers. And the O without the double bond, I was doing a demo to somebody of my cluster before I put together the talks or anything like that. And I'm like, it's not coming back. It's not coming back. Oh my God, it's broken. Here I am. I'm demoing it. Demo tests, the most stringent form of testing in the world. If it's going to break, it will break on a demo. And finally it came back, and I'm like, oh, okay, that makes sense. But at the time I was like, what broke? Anybody ever been there? Yeah, probably most of us. So I had my naive solution, and it works pretty well. For a first prototype, the naive solution is not bad. But if you remember, the same structure could be expressed in more than one way. It's kind of hard to grep for more than one thing at a time. You can do it. But PubChem, which is a database from the NIH, has a bitmap that's defined to describe a molecule. It's got 888 bits. Each bit defines a property of the particular molecule. For instance, if it's got greater than 2 carbon, then that bit would be set. If it's got greater than 4 carbons, then that bit would also be set. Boron would be another bit, if it's a ring, and so forth. So we could use fingerprints to define what our substances are. Smiles can be converted to a fingerprint, so we can still use a nice and easy way of describing what we're looking for. And then I was like, okay, if I create sets of substances with a particular bit set, I can take the intersection of those sets to find the substances which match our fingerprint. So you see how this is all kind of working up into this final case study. So my sets, I have 810 sets, one for each bit in the bitmap. If I use one file per bit in the bitmap, each has a list of the substances which have the bit set. If I use an unsigned 32-bit int, then my sets are of the files that are the set, anywhere from 4 bytes to 225 megabytes in size. Median is 9.3 million bytes. They average about 40. And my data set is 33 gigabytes total. So it's still quite a bit smaller than the 3 terabytes I had to begin with. But 33 gigabytes is quite a bit to be able to search through. So how can I optimize this? Well, one way that will help definitely is memoization. If you've solved something already, don't solve it again. Keep track of your solution. Keep track of what you've already done. Other optimizations. Start with the smallest set. Compare it with other sets. If you have a case where the majority of the substances have the property, well, flip it. That way you have a smaller set, and these are just ones that don't have the property. Again, we're trying to narrow down the data that we're searching through. As an aside, well, these are all bitmaps. Why not use bitmap tools? So in order to fit our universe of values, I needed a 10,000 by 10,000 1-bit PNG. These rank in size from 12K to 68 million bytes, or megabytes. Median's 1.7 meg, average is 2.4. So ImageMagick, which is an image processing tool on a 3.5 gigahertz box, requires 10 seconds per image. It's single-threaded. It only uses a single core. So if I use 5 cores, I could do 30 a minute, and in 20 years, I could pre-calculate everything. Brute force. I have a hammer. I'm going to use my hammer. No, we should use things that are a bit more intelligent. So that's the description of the problem that I've been working on with my pies. And I hope that you've enjoyed the journey. Real quick, the one data structure to rule them all. Anyone have an idea? It's in every single program. Yes, I'm looking for something more fundamental. I saw a hand. Yes, stacks are generally, but I'm looking for something even more fundamental than a stack. Binary, I don't know that that would be a data structure. In the top row? No, not a dictionary. Close. Bitmap's probably the closest. I'm looking for an array. You know, your stack can be is generally implemented as an array because your memory in the computer is an array. Every single data structure can be implemented as an array. As an aside, you know, to be done by the student, off time, etc., exercise for the student, I think, and this is my opinion, that it's a very good exercise to implement all of the fundamental data structures in an array, because you'll then have a much better understanding of what's happening at a low level in the computer. And it's an array. So I happen to like Markdown and MarkDeep in particular. MarkDeep handles things like math, handles the illustrations and so forth. And so this whole thing is just a single text file. And it does all the magic behind the scenes for me. I have a bunch of resources. I'll get the slides up. But we have general topics, bitmaps, cuckoos, searching, Galloping Search, Interpolation, Peacock, and so forth. And thank you. Any questions? All right. Now, I will say, one question that I have heard in the past is this the best search? You know, as we're going through each of the individual searches. And the answer to that, of course, is it depends on your data. So one time I gave this talk, and by the third time, somebody in the audience asked if this was the best search. The rest of the audience was shouting back in unison, "It depends on your data." So I hope you all enjoy the movie. Have a wonderful rest of your day, a wonderful rest of your conference. thank you to the vendors who have supported, as well as all the volunteers who make all of this work. In years past, I've been a volunteer. And this year, I'm kind of glad that I wasn't volunteering. It would have made life very interesting. But thank you. Enjoy your weekend. And I hope to see you all again.